Welcome to parametric surfaces and how to compute their areas. In this video, we'll compute the surface area of a sphere of radius r. So let's let S be the sphere, set of points with coordinates x, y, z, such that x squared plus y squared plus z squared equals some constant r squared. And we want to find the area of this sphere. Now, you probably memorized in elementary school the formula for the area, the surface area of a sphere, but now we want to actually calculate it using techniques of multivariable calculus. So how do we approach this problem? Well, we would like to introduce grid lines on the surface, as we see in this picture over here. And if you look at just one little region here, it looks almost like a parallelogram. And the more fine the partition is, the smaller that these little subregions are, the more and more they will look like parallelograms. They'll be very close to being parallelograms. And so we can approximate the area of one of these little subregions by calculating the area of its corresponding parallelogram. So let's suppose that here we have three-dimensional space, x, y, and z axes here, and somewhere out in space, it does not have to be horizontal nor vertical, it could be somewhere in between, we have a parallelogram. One of the sides of the parallelogram is the vector A, another side is the vector B, with an angle theta between them. And then we'll make copies of the vector B right here and a copy of the vector A right here so that we complete this quadrilateral a parallelogram. Let height be the perpendicular distance from this side up here down to this side here, this side over to this side. I drew H starting at this vertex so that we would have a nice triangle here to work with. So let's remember the formula for the area of a parallelogram, any parallelogram. The area of the parallelogram is equal to the length of the base times the height. In this picture, we can think of B, the length of this vector B, as being the length of the base, and the perpendicular height here is labeled as h. So the area then is the length of B, the norm of B, times h, the height. Now h is equal to a sine theta by just looking at this right triangle right here. And so basically what we have is the area is the norm of A times the norm of B times the sine of theta. If you remember a little bit of your vector algebra, this quantity right here is just the norm of the cross product of A and B. The area equals the norm of A cross B. So to attack this problem, let's remember that surfaces are defined by using two parameters to determine the x, y, z coordinates of a point on the surface. So we can think of a two-dimensional space here with axes u and v, and we will map some region down here into a region in three-dimensional space here with axes we'll call x, y, and z. And we'll let x be a function of u and v, let y be a function of u and v, and let z be a function of u and v. Some small rectangular area down here in the UV plane will be mapped into a region up here on this surface in three-dimensional space, and this little piece of surface looks a lot like a parallelogram. So in our sphere program, our problem, we're going to use not u and v, but something we're familiar with, theta and phi, coming from spherical coordinates. So we'll let x be a function of theta and phi, and that's equal to r sine phi cosine theta. Let y be r sine phi sine theta, and let z be r cosine phi. Let's remember what polar what spherical coordinates are. We're just using two of them for the angles here. Theta is an angle in the xy plane after you drop a perpendicular down to the xy plane. And phi here is an angle that is made with the positive z-axis. Theta can be anything between 0 and 2 pi, and phi can be anything between 0 and pi. Letting theta and phi range between those two limits I just mentioned will generate the entire sphere, both hemispheres. Now, in the theta phi diagram here, we could have a little region here, which is somewhere between u sub I and u sub I plus 1, and it's also between v sub j and v sub j plus 1. And this little looks kind of like a square here, but it doesn't have to be a rectangle. It maps into something over here in this surface, and perhaps it's this little parallelogram shaped piece right here. Okay, so we saw that we could define a surface parametrically by using two parameters. We call them in general u and v. So we have x, y, and z given in terms of u and v. We can write these three equations as one vector equation with a position vector for a point on that surface. R of uv is x of uv, y of uv, z of uv. This is a vector in three-dimensional space. When we map a small region, rectangular region, from the UV plane into 3 dimensions as we have here, it will map into, assuming that we have continuity conditions on the derivatives and so forth, it'll map into a region here that looks like a parallelogram. And in this case, if we start at this point right here, which we'll think of as the position vector r at u sub I, v sub j, we can find two vectors that kind of go along the two sides of this little subregion here. The length of this one is the partial of r with respect to u at the point u sub I, v sub j, times the change in u sub I, going from here to here. So delta u sub I is actually u sub I plus 1 minus u sub I. Similarly, if we change in the v direction, which in this case I guess is down here the way I've drawn this picture, this length here, actually this vector here, sorry, this is also a vector. This vector here is approximately the partial derivative of the vector function r with respect to v. Once again, at this point, u sub I, v sub j, the coordinates in terms of u and v, since r was given in terms of coordinates u and v also, times delta v sub j. So we have two vectors here emanating from this vertex of this region. We'll assume that this is very close to being a parallelogram, and we will use that formula we saw earlier to compute approximately the area of this little subregion by thinking of it as the area of a parallelogram, and that area can be computed by using a cross product. So we have these small parallelogram like little subregions in our surface, and it comes from mapping little rectangular regions in the UV plane over to here. So what we're going to do then is to approximate the area of these in terms of areas over here. So here's what we'll do. We'll say that A is the sum over all I and j of delta A sub ij, and this is approximately equal. Delta A ij here is going to be the area not of this region, not this exact area, but the approximate area using these two vectors that more or less go along the sides, and we'll think of these as two sides of a parallelogram. So for small regions here, which will correspond to small regions over here too, these things will almost be parallelograms somewhere out in space. So delta A sub ij, then, the area of that ijth parallelogram approximation, is the partial of r with respect to u at this point u sub I v sub j times delta u sub I. So that gives us this vector right here. Similarly, this second term in this cross product with the partial of r with respect to v at, once again, this point times delta v sub j is this vector right here. And so if we take the cross product of these two vectors and then take the norm of it, that will be the area of the parallelogram approximating the area of this subregion. So the area is approximately equal to this. And now we'll just change our notation a little bit. For this partial derivative with respect to u, we'll call it r sub u. With this partial of r with respect to v, we'll just call that r sub v. We can pull the constant factors, delta u sub I, delta v sub j, outside the norm, which we did here. And it looks like I just copied the same thing here again for some reason. But if we let the number of little rectangles here go to infinity by partitioning the region up here, this is going to be a Riemann sum for a double integral, which will give us the surface area of whatever surface we have up here. And so looking at this, we can see that in the limit, we'll get the exact area of that surface, A, being the double integral over the region R down here. Rij is just a little piece of that region. The norm of the cross product of those two vectors integrated with respect to u and with respect to v. This is using our double integral as an iterated integral notation. So now we get back to this sphere. Find the surface area of a sphere of radius r. So as we mentioned before, we're going to use as our two parameters for this surface theta and phi. The same theta and phi that hopefully you've learned about in some sort of course involving three-dimensional algebra. So we have x, y, and z being given by these formulas again, which means that the vector valued function r of theta phi that we're looking at is going to be this vector with x, y, and z coordinates in x, y, z space here, three-dimensional space. And theta can go from 0 to 2 pi, and phi can go from 0 to pi. Phi, remember, is the angle that our position vector makes with the positive z-axis. So we're going to do this computation using SageMath. We're going to compute the surface area of a sphere of radius r, and we'll do, as I mentioned, the calculation basically in spherical coordinates. We'll use the two angles from spherical coordinates as our parameters. So the first thing I'm going to do is to define some variables which we'll use down here somewhere. So I'm going to define variables rho, r, capital R, phi, theta, x, y, and z. After making some changes here, re-editing, I think I never actually used the variable rho here. R is going to be the radius of the sphere. Capital R is going to be the position vector for a point on the surface of that sphere. Phi and theta are the angles in spherical coordinates. X, y, and z are the three coordinates in rectangular coordinates. So we execute this statement, and these variables are now defined. So the next thing we'll do is define x, y, and z in terms of those spherical coordinates, remembering that we're just considering one sphere and it has radius little r. So x then is r sine phi times cosine theta, and let's show what x is. It's r times cosine theta sine phi. We'll let y be r sine phi times sine theta, and let's show what y is. And here's the output here, r sine phi sine theta for y. And z is then going to be r times cosine phi. We'll show what z is. It's r cosine phi. No surprises there. So now what we'll do is put x, y, and z into a vector, a position vector, which we'll call capital R. Capital R is the vector with components x, y, and z. And let's see what R looks like. Show R. So R is this vector here, this position vector. R cosine theta sine phi is the x coordinate. R sine phi sine theta is the y coordinate. R cosine phi is the z coordinate. The next thing we're going to do is to differentiate r with respect to theta. We're going to calculate the partial derivative of r with respect to theta. So to differentiate it, we'll use the command diff. We're differentiating that vector valued function with respect to theta, and then we're showing what this function r theta, that's the name I give to this derivative, show what that is. And it turns out to be minus r sine phi sine theta, r cosine theta sine phi, and 0. We can see that pretty easily. We can verify that by looking up here. Here's the vector r. If you differentiate each of these three components with respect to theta, let's see, the derivative of cosine theta is minus sine theta. So the derivative of this component is just minus r sine theta sine phi sine theta. Okay. Yeah. Okay. The y coordinate is r sine phi sine theta. I just put these two factors in different order than I had here, didn't I? Okay. When you differentiate this with respect to theta, what's going to happen? The derivative of sine of theta is cosine of theta, and that's what we have right here. Okay, for this third one, if you differentiate this with respect to theta, well, you notice there's no theta in here. There's just a phi. So the derivative of this, partial derivative of this with respect to theta, is just 0. Okay, so the partial of r with respect to theta is this vector. So let's continue with our calculation. We also need to calculate the partial derivative of that position vector r with respect to phi. And later we're going to take the cross product of those. So to do that, we have to differentiate r with respect to phi. And I'm going to call this partial derivative r phi. A very imaginative name for that, isn't it? And then we'll show what r phi is. Well, once again, if we differentiate r with respect to phi, we're going to differentiate the x component, the y component, and the z component separately for phi. And when we do, we will get r cosine phi cosine theta, r cosine phi sine theta, and minus r sine phi. Now, the next part is to calculate the cross product of the partial derivative of r with respect to theta, crossed with the partial derivative of r with respect to phi. And here is where SageMath comes in handy, because this cross product otherwise would take a little bit of paper, I guess, and pencil, ink, whatever you use. But in any case, we can do it on the computer pretty easily using SageMath. Here's what's going to happen. I'm going to let W be this cross product. I have to give it a name to use later. And if we look at this, this looks kind of strange. We have r theta dot cross product with r sub phi. So what this does is it takes the cross product, which is the cross product of r theta, which is right here, and r phi, which is right here. And it stores whatever this is, the result, in the variable w. And so we'll show w. We'll show what the cross product is. And here it is right down here. And as you can see, it looks kind of complicated, doesn't it? So we're not going to spend time on that, but this is the cross product. So then let's take the norm of this cross product. So I want to show w dot norm, and I want to simplify it fully. When we simplify that, it turns out to be the square root of r to the fourth times sine squared of phi. Now, let's look at this for 1 minute. This actually simplifies a little bit further because we know something about phi. Phi, remember, is between 0 and pi. And so the sign of phi is not negative. It's non-negative. So the square root of the sine squared of phi is just going to be sine of phi. The square root of this other factor, r to the fourth, is going to be r squared. So this actually simplifies in our particular problem to r squared times sine of phi. So now to find the area, we have to integrate that norm of that cross product over the region in the UV plane, and we'll be integrating it with respect to theta and phi in this case. So if you look at the integral here, we have the integral of the integral, because it's a double integral, of r squared sine phi. That was just the square root of this stuff here. And we're integrating it where theta goes from 0 to 2 times pi. And whatever this integral turns out to be, we're then integrating it again, this integral, where phi goes from 0 to pi. And then we want to see what the area of this is. Remember, area equals this stuff. So I'll put a show statement in here to display the results. Show the string surface area equals, and then whatever the area was that we computed up here. When you execute this statement, what we get is this output. The surface area is 4 pi r squared. Now, this is a formula that you probably learned many years ago, probably in elementary school, I suspect, if they still teach it there. But now we can see how that formula came about. You probably were just given the formula and the teacher said, just use it, plug in numbers to solve these problems. But now we see that we can actually derive the formula for the surface area of a sphere. And similarly, by using triple integrals, we could derive the formula for the volume of a sphere. I hope you enjoyed this video, and please stay tuned for more to come. Have a good day.